What if a galaxy could pull another galaxy toward it, like a slow cosmic tide, far beyond our own sky? The Whirlpool Galaxy is doing exactly that. Its spiral arms glow with newborn stars, while a smaller companion galaxy tugs at its edges, shaping a dance that has lasted millions of years. Tonight, on Fall Asleep to Astronomy, we will drift gently toward the whirlpool's bright center, letting the swirl of starlight guide us. There is nothing to solve here and nothing to hurry. Only a quiet journey into one of the universe's most elegant storms. If this calm wandering brings you peace, a soft like and quiet subscribe. Help others find their way. For now, settle in and let the night open around you as we begin. Far beyond our own sky, the Whirlpool Galaxy turns slowly in the dark, a vast spiral of stars, gas, and dust. It rests around a few tens of millions of light years from Earth, close enough that we can trace its swirling pattern, distant enough that each shimmer in its arms is an entire sun. Those arms cradle billions of stars, quiet nurseries where new suns are forming, and the faint ashes of stars that have already burned out. To imagine drifting toward its center is to picture falling into a region where gravity grows fierce, where star clusters tighten, and where glowing clouds of gas are busy building the next generation of light. Astronomers know this galaxy by several names: the Whirlpool, Messier 51, and NGC 5194. It belongs to a class called a grand design spiral, meaning its arms are not ragged or broken, but clearly drawn and gracefully symmetric, curling outward like careful brushstrokes. Deep at the core lies an active heart, a Seyfert Type II nucleus, where a supermassive black hole is wrapped in clouds of heated gas. That gas glows as it falls inward and stirs, turning the center into a compact, brilliant storm. You can find the Whirlpool in the small constellation Canes Venatici, the hunting dogs, near the curved handle of the Big Dipper. It is somewhat smaller than our Milky Way, but still stretches across tens of thousands of light years and contains well over 100 billion times the mass of the Sunday. The Whirlpool does not travel alone. A smaller companion, NGC 5195, drifts so close that the two are tied together by gravity. They pull at one another, stretching out faint bridges and streams of stars and gas. Under a dark sky, ordinary binoculars show the Whirlpool as a soft, hazy patch. A small telescope separates the pair into two distinct glows. With larger instruments and very clear nights, delicate hints of the spiral pattern appear, and small knots of brightness mark regions where stars are being born. For astronomers, this pair is a natural laboratory. Because the Whirlpool and its companion are both nearby and sharply defined, they have become one of the clearest examples of how galaxies interact and reshape each other. The human story with this galaxy began in the late 18th century. In the year 1773, the French astronomer Charles Messier noticed a faint, fuzzy object while hunting for comets and added it to his list as Messier 51. Many decades later, in the 19th century, the Irish astronomer William Parsons turned one of the largest telescopes of his time toward that same blur. There, he sketched a spiral shape, the first clear drawing of such a pattern in the sky. People still believed these spirals were clouds within our own galaxy, not separate systems. Only in the early 20th century did Edwin Hubble show that these spiral nebulae are, in fact, other galaxies, far beyond the Milky Way. He used special pulsing stars, Cepheid variables, as distance markers to reveal just how far away they truly are. Later, with the rise of radio astronomy, scientists saw that Messier 51 and its companion are not only close in the sky, but also physically linked. Their gas and stars tugged and twisted by their mutual pull. Today, when astronomers speak of Messier 51, they often mean the entire system, the main spiral, called M51A, and the smaller dwarf, M51b. Modern telescopes have deepened this picture. Sensitive instruments showed that the bright core of the whirlpool is not simple, but contains multiple components, hinting at a complex central structure. In the year 2005, the Hubble Space Telescope captured a detailed portrait of the galaxy, revealing dark lanes of dust threading through its luminous arms, pinkish clouds where new stars are forming, and bright clusters of young, blue-white suns scattered like tiny embers. The galaxy's disk is likely a few 100 million years old enough to hold the traces of many cycles of star birth and star death, yet still young and sharply patterned. At the very center sits the supermassive black hole, the hidden anchor of the galaxy. For many years, it was thought to be wrapped in a smooth ring of dust. Newer observations suggest something subtler. The dust obscures part of the region rather than circling it in a perfect band. From this crowded heart, narrow cones of ionized gas extend outward, like pale beams, marking pathways where energy escapes back into space. The whirlpool's arms are especially striking. They curl outward in a graceful clockwise sweep, but one arm bends in an unusual way, as if it had been gently pulled off course. Astronomers believe this odd kink is a scar from the close embrace with its companion galaxy. Simulations suggest that the smaller NGC 5195 may have passed through the whirlpool's disk more than once, first emerging from behind, plunging through, and looping around again. Today, it appears slightly behind the main galaxy, from our point of view, locked with it in a slow gravitational waltz. These encounters have drawn out delicate tidal features, long plumes and streams of stars and gas that reach far beyond the obvious spiral. One extended feature, known as a northwest plume, seems to have been pulled from the whirlpool's own disk and now arcs far from the center. Other, bluer plumes and faint wisps mark further signs of this long-running tug-of-war. Together, they paint a picture of a galaxy that has been shaped and reshaped by its neighbor over hundreds of millions of years. Inside the whirlpool, especially toward its central regions, stars are forming at a brisk pace. The galaxy is turning gas into new suns with an efficiency comparable to our Milky Way, but concentrated in a narrower zone. This period of heightened activity will eventually calm as the gas is used up or heated, but for now, the arms gleam with young stars, their light tracing out the spiral like fresh strokes of paint. The galaxy has also hosted several dramatic stellar endings. Over the past decades, astronomers have watched multiple supernovae flare briefly within its arms, each marking the death of a massive star. One exploded after losing much of its outer layers, another as a more typical hydrogen-rich giant, and yet another showed signs that its source was a rare yellow supergiant. In the year 2019, observers recorded a different kind of event, a luminous red nova likely created when two stars merged into one, glowing warmly through surrounding dust before fading back into darkness. When scientists study the gas within the whirlpool, they find a rich chemistry. Various molecules trace the densest clouds where stars are forming, and certain more fragile species appear only near the center, suggesting that the heart of the galaxy offers special conditions of density, warmth, and radiation. There are even hints of planets. Using X-ray observations, astronomers have identified a candidate world, possibly somewhat smaller than Saturn, that may orbit a compact, bright X-ray source made of a dead star and a massive companion. If this candidate is confirmed, it would be one of the first known planets beyond our home galaxy, quietly circling in the deep space around a stellar remnant. The Whirlpool and its companion belong to a small local group of galaxies that includes the Sunflower Galaxy and a few other neighbors. This group may be part of a larger chain stretching across space, linking to other gatherings. Even on these vast scales, galaxies keep company with one another. They rarely live alone. Yet, a galaxy is more than a cluster of stars living in the same place. It is a layered ecosystem of stars, gas, dust, and something we cannot see at all. What truly seems to distinguish a galaxy from a simple star cluster is the presence of dark matter, an invisible form of mass. In a star cluster, the gravity that holds the system together comes almost entirely from the stars you can see. If enough stars drift away, the cluster eventually dissolves. In a galaxy, there is something extra. A halo of dark matter surrounds the visible disk like a ghostly shell. It deepens the gravitational well, shapes the orbits of stars, helps pull in and hold gas, and protects the galaxy from being easily torn apart by the tides from larger neighbors. Without this unseen halo, a galaxy-sized group of stars might quickly lose its structure. Dwarf galaxies, even the faintest, appear to carry this hidden scaffolding. Larger galaxies tug on them, stretching and distorting their shapes, sometimes stripping away outer stars and leaving long trails across the sky. Yet many dwarfs endure for billions of years, still bound together because their dark matter halos give them the strength to survive these encounters. This durability is one of the clues astronomers use when deciding whether a small, dim system is really a galaxy or simply a cluster. The faintest known galaxies, sometimes called ultra-faint dwarfs, blur the line even more. They contain only a few thousand stars spread over large regions, so their light is barely there. If only the visible stars were present, the internal motions would not make sense. The stars move as though something far more massive is pulling on them. That something, again, appears to be dark matter. In this way, even ghostly smudges of light can qualify as galaxies if they sit in deep, dark matter wells. How stars are born and what their chemical fingerprints look like offers another clue. Galaxies behave like long-lived nurseries, where gas clouds can collapse again and again to form new generations of stars. As older stars die and explode, they enrich the gas with heavier elements, and younger stars carry more complex mixtures in their atmospheres. Star clusters, in contrast, usually form in a single burst. Once their gas is used up, they cannot make new stars, and their chemical story remains largely frozen in time. There are exceptions here as well. Omega Centauri, a massive cluster in our own Milky Way, shows a mix of stellar chemistries more typical of a small galaxy. Many astronomers suspect it is the stripped core of a dwarf galaxy that lost its outer stars and much of its dark matter long ago. By measuring how stars move in such systems, scientists can estimate how much visible mass exists and compare it to the gravity required to hold everything together. If stars move too quickly for the visible mass to explain, dark matter is likely present, and the object is more galaxy than cluster. Even with all these clues, the definition remains a little soft, because violent interactions can strip away dark matter and blur the boundary between what we call a galaxy and what we call a cluster. Some astronomers also point out that even star formation is not a perfect guide. A galaxy can exhaust or lose its gas and stop making new stars, yet still be very much a galaxy. What most agree on, though, is that galaxies are not simple piles of stars. They are restless, layered environments that grow, change, and sometimes slowly fade. They are shaped by light and by shadow, by ordinary matter and by the invisible weight of dark matter. Trying to draw a sharp line between a galaxy and a cluster is like trying to draw a border in a slowly shifting mist. If the definition is made too strict, we risk ignoring tiny, ancient systems that may hold clues to the very first galaxies. If it is left too loose, we blur what makes galaxies so special as coherent, long-lived structures. Some of the faintest known galaxies, barely more than ghostly smudges against the dark, live right on this boundary. They look delicate, almost uncertain, as if they might be a bridge between what we call a galaxy and what we call a cluster, rather than neatly fitting either word. If the great spiral and elliptical galaxies are like bright cities of light, then dwarf galaxies are their quiet, scattered villages. They are small and faint, easy to overlook, yet far more numerous than the showy giants. They do not blaze with grand spiral arms or immense glowing bulges. Instead, they are sprinkled across the universe in soft abundance, like dim lanterns hung along the threads of the cosmic web. When astronomers count how many galaxies there are, most of them turn out to be dwarfs. Compared to a large spiral like the Milky Way, which holds hundreds of billions of stars, a dwarf galaxy might contain only a few billion, a few million, or even only a few thousand. Some of the tiniest known could hide comfortably inside a single spiral arm of a big galaxy. Others are puffed up and diffuse, their stars stretched over wide regions so thinly that they almost disappear into the background. Their sizes can span only a few thousand light-years, a fraction of the reach of a grand spiral disk. What they tend to share is a lack of polished structure. Dwarfs do not usually have the smooth spirals of Andromeda or the bright, rounded glow of giant ellipticals. Instead, they look uneven and irregular, with crooked outlines, scattered knots of light, and gas clouds that seem torn or frayed, as if a sculptor had left the work half-finished. Part of this untidy appearance comes from their weakness. With far less mass than large galaxies, their gravity is not strong enough to hold their contents tightly in place. Encounters with larger neighbors can tug at them easily, twisting their shapes and stripping away gas and stars. Many dwarf galaxies orbit bigger galaxies as satellites, circling in loose swarms. The traces of these encounters are written across their forms. Some dwarfs are stretched into long, thin arcs. Others have holes in their gas, carved out by supernova blasts and tidal forces. Yet, despite their fragility, these small galaxies are deeply important. Astronomers think they were among the first structures to take shape in the early universe, long before majestic spirals emerged. Tiny clumps of gas and dark matter gathered into the first dwarfs, which then collided and merged over immense spans of time to build the massive galaxies we see today. Some dwarfs survived these chaotic ages and still circle their larger companions, carrying memories of conditions that existed when the universe was young. Not all dwarfs share the same look or life story. Some, called dwarf spheroidals, are extremely dim and diffuse. They have only a modest number of stars spread over a wide region, almost no gas, and little or no ongoing star formation. They are like pale fossils, the glowing embers of a fire that burned long ago. Others, known as dwarf irregulars, are more lively. They contain clouds of gas and pockets where stars are still being born. In these regions, the light of hot, young stars illuminates the surrounding gas, carving out small, bright patches. There are also dwarf ellipticals, smoother and more rounded than irregulars, but still far smaller and less luminous than the giant elliptical galaxies that dominate some clusters. In general, dwarf galaxies are poorer in heavy elements than large galaxies. Heavier elements are forged inside stars and released into space when those stars die, especially in powerful supernova explosions. In a big galaxy, gravity is strong enough to hold on to much of that enriched gas, allowing later generations of stars to form from material that has already been processed. In a dwarf, the gravitational grip is weaker. The fierce winds from massive stars and supernovae can blow enriched gas out into intergalactic space. As a result, the gas that remains is more primitive, closer to the simple mix that filled the early universe. By studying dwarfs, astronomers can glimpse what conditions were like before galaxies such as the Milky Way became chemically rich and complex. Even though dwarfs carry far fewer stars, they often seem to be especially dominated by dark matter. Pound for pound, they can hold more invisible mass compared to the light we see than giant galaxies do. This hidden weight acts as a deep but unseen well, helping them survive the gravitational pulls of their environment, despite their faintness. Because their structures are so delicate and their visible matter so sparse, small changes in dark matter leave noticeable marks. For this reason, astronomers sometimes call dwarf galaxies laboratories for dark matter, places where its subtle effects can be studied with unusual clarity. Our own Milky Way is wrapped in a small retinue of such companions. Two of the most famous are the Large and Small Magellanic Clouds, visible as misty patches in the southern sky. They are irregular, gas-rich dwarfs filled with young stars and active star-forming regions, currently interacting not only with the Milky Way but also with each other, tugging on their gas and stretching out streams between them. Closer in, astronomers have identified several tiny, faint dwarf spheroidals that orbit our galaxy. Some are so diffuse that, at first glance, they are almost indistinguishable from the random sprinkling of background stars. Other large galaxies host their own families of dwarfs. Andromeda, our nearest giant neighbor, has dozens of known satellites, both irregular and spheroidal, forming a miniature system around it. Astronomers suspect that many more dwarf companions remain hidden, too faint or too spread out to have been noticed in older surveys. As instruments grow more sensitive, new members of these extended families continue to appear. Though they are small, dwarfs can have surprisingly large effects on their hosts. When a big galaxy swallows a dwarf, the infalling gas can trigger bursts of new star formation, while the stars from the dwarf are stirred into long, graceful streams that wrap around the larger galaxy. The Milky Way's halo contains several such stellar streams, silent rivers of stars that are thought to be the remains of dwarfs torn apart over billions of years. Some dense star clusters may, in fact, be the stripped cores of ancient dwarfs, the last compact remnants of galaxies that were almost entirely consumed. According to detailed computer simulations built on the idea of dark matter halos, galaxies like the Milky Way should be surrounded by hundreds, perhaps even thousands, of tiny companions. In these models, dark matter clumps into countless small halos. Many of those halos are expected to cradle dwarf galaxies, especially in the early universe. Yet, when astronomers look around our own galaxy with telescopes, they find only a few dozen dwarfs. The same is true around Andromeda, and in other environments. This mismatch between prediction and observation is known as the missing satellites problem. At first, many researchers wondered whether the solution might simply be that the dwarfs are there, but too faint to see. As technology improved and digital sky surveys reached deeper limits, more tiny galaxies were indeed found. Projects such as the Sloan Digital Sky Survey and other wide-field efforts revealed a population of ultra-faint dwarfs whose stars barely rise above the background. Later surveys added more, particularly in the southern sky. Each new discovery narrowed the gap between models and reality, but did not erase it. There still seemed to be far fewer visible satellites than the simplest versions of the simulations predict. This led astronomers to consider that perhaps many small dark matter halos never managed to light up at all. In the early universe, intense radiation from the first stars and active galactic nuclei may have heated and pushed gas out of the smallest halos before it could cool and form stars. In those that did manage to begin forming stars, early supernova explosions might have blown away what little gas was left. In that picture, countless halos remain dark, empty of stars and invisible to us, while only a fraction shine faintly as the dwarfs we can detect. Another possibility reaches deeper into the nature of dark matter itself. The standard view assumes that dark matter is cold, moving slowly in the early universe and gathering easily into small clumps. But if dark matter were slightly warmer, moving faster, it would have smoothed out the tiniest structures and reduced the number of small halos from the beginning. Or if dark matter particles can interact with one another in subtle ways, they might erase some of the smallest clumps over time. These ideas remain speculative, but the missing satellites problem is one of the strongest hints that something in our understanding of either galaxy formation, dark matter, or both is incomplete. To untangle these threads, astronomers look not only for intact dwarf galaxies, but also for the ghostly traces of those that have already been destroyed. Long, thin, stellar streams looping around the Milky Way reveal where satellites once orbited before being torn apart. By counting both the survivors and the remnants, scientists can better estimate how many dwarfs there truly were and how many might still be unseen. In the early days, finding a dwarf galaxy was often a matter of patient luck. Astronomers pored over photographic plates, noticing tiny, fuzzy patches that were not quite like star clusters. It was hard to be sure what these smudges were. As digital imaging arrived, the search changed. Wide-field surveys began to map large areas of the sky in fine detail, reaching down to very low surface brightness. One of the most influential of these is the Sloan Digital Sky Survey, which used a dedicated telescope in the high desert of New Mexico to scan enormous swaths of the sky. Within its vast sea of data, astronomers found small regions where there were just a few more stars than expected, faint overdensities that, when examined closely, turned out to be dwarf galaxies hiding in plain sight. What once vanished into the background of the sky can now be coaxed into view with patterns in data. Instead of hunting only for a small glowing cloud, astronomers learned to search for tiny rises in the number of stars in a region. On a graph, a dwarf galaxy might appear not as a bright peak, but as a gentle bump in the star count. Those modest bumps, easy to miss at first glance, became the fingerprints of hidden companions circling our own galaxy. Around the crowded disk of the Milky Way, this approach is especially powerful. Our galaxy contains hundreds of billions of stars, making the sky noisy and confusing. Yet within that sea, a dwarf galaxy can stand out through the shared traits of its stars. They might be older, dimmer, or redder than typical Milky Way stars. By carefully filtering for these particular kinds of stars, astronomers can separate the faint whisper of a dwarf galaxy from the overwhelming background glow. Some of the faintest galaxies found in recent decades are so delicate that they stretch the meaning of the word galaxy. These ultra-faint dwarfs contain so few stars that, if you were standing inside one, the sky might look almost the same as it does from Earth. No bright band would give away your location, only scattered points of light. To uncover such fragile systems, astronomers rely on very deep, sensitive sky surveys that reach far beyond what the unaided eye can ever see. One major survey, using a telescope with a mirror about 4 meters across in the high mountains of Chile, revealed dozens of these ultra-faint dwarfs gently orbiting the Milky Way. Modern instruments do more than collect images. They can confirm whether a suspicious little grouping of stars is truly a galaxy. A chance cluster will have stars moving in many directions, each following its own path. In a real galaxy, the stars move together, held by a common gravitational pull. With sensitive spectrographs, astronomers measure tiny shifts in the color of starlight, subtle fingerprints of motion. If the stars in a faint patch share similar speeds, it suggests that an unseen mass is binding them. Dark matter, acting as invisible glue, marks the system as a true galaxy rather than a loose association. In this way, the presence of hidden matter reveals itself through the quiet choreography of a few scattered stars. The Hubble Space Telescope has been a gentle but crucial helper in this search. Floating above Earth's unsteady atmosphere, it can resolve individual stars in distant, faint dwarfs with remarkable clarity. By examining how bright and how colorful these stars are, astronomers can estimate their ages and histories and confirm whether they belong to a small, ancient galaxy or are simply part of the Milky Way's foreground and background. And the search is still unfolding. New observatories are being built to watch the sky again and again, night after night, creating a living map of the universe. A survey known as the Legacy Survey of Space and Time will scan large regions repeatedly, making it possible to spot even subtler structures and track how these dim companions change over the years. Looking for dwarf galaxies has become something like listening for the faintest echoes in a vast, quiet hall. Each time a tiny smudge of light proves to be a real galaxy, our picture of the hidden structure of the cosmos grows a little more precise and a little more wondrous. All around the Milky Way, like bees circling a great hive, smaller galaxies move in slow, silent orbits. These satellites come in many forms, some bright and busy with young stars, others dim and ghost-like. Together, they form a family that helps tell the story of how galaxies grow, collide, and change with time. The most familiar of these companions are the two Magellanic Clouds, the Large Magellanic Cloud and the Small Magellanic Cloud. For people in the southern hemisphere, they appear as pale, misty patches in the night sky, visible even without a telescope. The Large Magellanic Cloud, often called the LMC, is the heavyweight among the Milky Way's companions, containing tens of billions of stars and standing as a modest galaxy in its own right. Its smaller sibling, the Small Magellanic Cloud, or SMC, holds only a few billion stars, yet still shines more brightly than nearly any other dwarf nearby. Neither of these clouds looks like a perfect spiral or a smooth oval. They are irregular, like torn pieces of a larger painting. Their shapes hint at long histories of gravitational tugging, both from each other and from the Milky Way. They are rich in gas, and within them lie vast regions where new stars are being born. Great nebulae glow in their depths, lit by clusters of hot young stars that have only just emerged from their birth clouds. Beyond these bright companions lies a quieter crowd of fainter satellites, known as dwarf spheroidal galaxies. They contain only hundreds of thousands to a few million stars, spread so thinly that they look almost transparent. They hold little or no gas, and star formation within them has long since stopped. These galaxies are ancient and subdued, made up mostly of old, fading suns. Names such as Sculptor, Fornax, and Carina mark some of these dim companions, each one circling the Milky Way tens to hundreds of thousands of light years from the center. Some satellites are caught in especially dramatic moments. The Sagittarius dwarf galaxy, discovered in the 1990s, is one such example. It is plunging through the Milky Way's disk and is being slowly torn apart. Its stars are drawn out into long, graceful streams that wrap around the galaxy, tracing loops across the sky like ribbons of faint light. Another small companion, the Canis Major dwarf, appears to be meeting a similar fate, with its stars stretched into arcs around the outer regions of our galaxy. These fragile systems show that a galaxy's edge is not a hard boundary. Stars can be stolen, gas can be stripped, and once separate galaxies can be folded into one another. When astronomers chart the known satellites of the Milky Way, they find a family extending outward for hundreds of thousands of light years. Some companions in the constellation Leo and elsewhere orbit far from the galactic center, near the region where the Milky Way's gravitational hold begins to compete with that of the Andromeda galaxy. Even so, these distant dwarfs remain bound, following immense, slow paths that can take billions of years to complete. Astronomers sort these companions in many ways. Gas-rich irregular dwarfs, like the Magellanic Clouds, are bright and rare. Gas-poor spheroidals are far more common, but so faint that they often vanish into the background. Ultra-faint dwarfs, some with only a few hundred or a few thousand stars, push the very edge of what we are willing to call a galaxy at all. Together, they form a smooth spectrum, from active, star-forming clouds to ancient, nearly extinguished relics. If we could somehow dim the bright glow of the Milky Way's main disk and look only at the vast halo surrounding it, the view would not be empty. Instead of smooth darkness, we would see something that looks like a spider's web made of starlight. Thin, delicate strands stretching across enormous distances. These are stellar streams, the remnants of smaller galaxies and clusters that have been pulled apart by the Milky Way's gravity. Each stream is a ghostly scar of a past encounter, a record of a satellite that once orbited whole, but has since been unspooled into a thread of stars. Imagine a small galaxy passing too close to the Milky Way. At first, its stars hold together under their own gravity, but as it swings around our galaxy again and again, the difference in gravitational pull from one side to the other slowly works on it. Over millions of years, the small galaxy begins to unravel. Stars peel away from its leading and trailing edges, forming two long tails that wind around the Milky Way like faint bands of light. What was once a single compact object becomes a narrow, shimmering stream, almost indistinguishable from the background, unless you know precisely how to look. The Sagittarius stream is one of the most striking examples, wrapping almost completely around the sky. Other streams, such as those associated with the cluster Palomar 5 or with small lost companions, tell similar stories. Some came from dwarf galaxies, others from globular clusters, but all of them are fossils, preserving the paths of systems that no longer exist in their original form. By mapping their positions and motions, astronomers can reconstruct how the Milky Way has slowly built itself up over billions of years by consuming smaller neighbors. These streams also whisper secrets about dark matter. If the Milky Way's dark matter halo were perfectly smooth, the streams would form gentle, unbroken curves. Instead, many appear kinked or distorted, as if something unseen has bumped or tugged on them. Those disturbances may come from compact clumps of dark matter, small halos that never formed visible galaxies. In this way, stellar streams act as natural detectors, allowing scientists to probe the hidden shape and lumpiness of the dark halo surrounding our galaxy. Over time, each stream grows longer and more diffuse. The stars spread out, and the once clear ribbon fades into the general halo. Before that happens, though, the stream offers a precious chance to read one more page from the Milky Way's history. Some astronomers picture the halo as a vast archive, with each stellar stream as a document preserving a chapter on how our galaxy became what it is. Within this busy, changing environment, the Large Magellanic Cloud stands out as something special. It is not merely a small follower trailing in the Milky Way's wake. With its sweep of stars, glowing regions of gas, and spiral-like patterns in its disk, it looks like a miniature spiral galaxy in its own right. For anyone standing in the southern half of Earth, it appears on clear nights as a faint, milky patch, visible with no telescope at all. People have noticed it for thousands of years, long before it had a name, and it has guided travelers and inspired stories across generations. The Large Magellanic Cloud is bright and rich in structure. Among all the Milky Way's companions, it is one of the most massive and striking. Its total mass in stars is roughly 1/10 that of the Milky Way, a huge amount for a satellite. Like other galaxies, it is wrapped in a halo of dark matter, an invisible framework that helps hold it together even as it moves through our galaxy's powerful gravitational field. Without that hidden support, repeated pulls might have torn it apart long ago. When astronomers look closely, they see a bright bar of stars forming its central spine, with spiral features curling outward, giving it the look of a small barred spiral galaxy. It seems to live between two identities, massive and structured enough to resemble an independent spiral, yet still clearly bound to the Milky Way. Inside the Large Magellanic Cloud, star formation is vigorous. Compared with many nearby galaxies, including our own, the rate of new star birth is remarkably high. At the heart of this activity lies the Tarantula Nebula, one of the brightest and most famous stellar nurseries in the sky. This immense cloud of gas and dust stretches for hundreds of light years. Within it, newborn stars form in swarms, some among the most massive and luminous ever observed. Their fierce radiation lights up the nebula, carving out intricate shapes and glowing filaments. The Large Magellanic Cloud has also been the stage for some of the most important stellar explosions seen from Earth. In the year 1987, a star within this galaxy ended its life in a supernova now known as Supernova 1987A. It was the closest such event observed in modern times, bright enough to be seen with the unaided eye from dark locations. For astronomers, it offered a rare, almost real-time glimpse into the death of a massive star, how its core collapses and how its outer layers blast into surrounding space. That brief, brilliant flare, unfolding in a small galaxy just beyond our own, became one of the most studied events in the history of astronomy, and it happened right inside this remarkable neighboring world. Unlike many small galaxies that have already lost most of their gas, The Large Magellanic Cloud still carries generous reserves of hydrogen, the raw fuel for making new stars. That richness may come from its relatively large mass, or from the path it has taken through space. Some studies suggest that the Large Magellanic Cloud is only now making its first close approach to the Milky Way, moving too quickly to have spent billions of years in a quiet orbit. If that is true, we are seeing it at a special moment, just as it begins to feel the full pull of its giant neighbor. In this picture, the Large Magellanic Cloud is not an ancient obedient satellite, but a bold visitor, a once independent galaxy that has only recently crossed into the Milky Way's gravitational territory, perhaps bringing along its own tiny companions. The pull between the two is not one-sided. The Large Magellanic Cloud is massive enough to tug back, nudging the motions of stars in the Milky Way's disk, and possibly warping the shape of our galaxy's dark matter halo. Between them stretches a long ribbon of gas called the Magellanic Stream, a vast trail drawn out of both the large and small Magellanic Clouds by tidal forces. One day, much of that gas may rain down onto the Milky Way, feeding it with fresh material and sparking new waves of star formation. If the Milky Way were smaller, or the Large Magellanic Cloud a little farther away, we might not call it a satellite at all. It lives in a gray area, blurring the tidy labels astronomers like to use. Nature is rarely interested in our neat categories. Galaxies, like people, arrive in many in-between forms. For humans, the Large Magellanic Cloud has always been more than a case study. Long before telescopes, sailors and storytellers in the southern hemisphere wove its soft glow into their maps and myths. Even today, with modern instruments that can count its stars and trace its history, it remains both familiar and mysterious, close enough to feel almost within reach, yet distant enough to remind us how big the universe truly is. Nearby drifts its smaller sibling, the Small Magellanic Cloud, a far more chaotic companion. Unlike its larger neighbor, it shows no clean spirals or smooth oval. Instead, it appears lopsided and irregular, a broken patch of light rather than a neatly built structure. The reason lies in where it lives. The Small Magellanic Cloud is trapped in a constant gravitational tug-of-war between two giants, the Large Magellanic Cloud and the Milky Way. Pulled in different directions at once, it has been reshaped again and again. The Small Magellanic Cloud sits at a distance of around 200,000 light-years, making it one of the closest galaxies beyond the Milky Way. It contains only a few 100 million stars, a tiny population compared with the Large Magellanic Cloud, and minuscule beside our own galaxy. Yet its nearness gives astronomers an extraordinary chance to watch it change. They can trace the motions of its stars, see how its gas is stretched and twisted, and follow how its outline shifts over time. Rather than a tidy disk, the Small Magellanic Cloud looks like a tangled pattern of denser clumps and empty gaps. One part forms a compact main body, while another stretches outward like a wing being pulled from a bird in flight. This wing-like extension is thought to be the scar of a close encounter with the Large Magellanic Cloud. During that meeting, the stronger companion pulled away part of the Small Magellanic Cloud's material, leaving behind a trailing structure extending far into space. Gravity's long, invisible fingers have literally pulled it out of shape. The two Magellanic Clouds are so near one another that they travel together, bound by their shared gravity as they move through the Milky Way's outer regions. Over immense spans of time, they have likely circled each other in a slow, intricate dance, while drifting ever deeper into our galaxy's influence. Because the Small Magellanic Cloud is lighter, it bears the most visible marks of this partnership. It has lost more gas, been more dramatically distorted and shows more obvious scars from past encounters. Radio telescopes reveal an even grander structure tying the pair together: the Magellanic Bridge, a luminous rope of stars and gas stretching between the large and small Magellanic Clouds, as if the two galaxies were holding hands across the void. Gas drawn out of the small Magellanic Cloud was squeezed and compressed along this path, and in that compressed gas, new stars were born. Young, bright blue suns now shine along the bridge, proof that it is not just a dead connection, but a living place of creation, where torn material has become the cradle for fresh light. Beyond the bridge lies the far larger Magellanic Stream, which trails behind the clouds like a ghostly ribbon. It is made mostly of hydrogen gas and stretches for hundreds of thousands of light years, longer than the Milky Way's disk is wide, too faint to see with human eyes. It becomes clear when radio telescopes tune in to the specific frequency at which neutral hydrogen glows. The stream tells the story of repeated close passes between the Magellanic Clouds and the Milky Way. Each approach pulls more gas loose, adding to the long, curling tail that wraps around much of the southern sky. Gas is the lifeblood of galaxies, the raw material from which new stars are born. As the Magellanic Clouds lose gas into the stream, their ability to form stars slowly declines. In time, much of this stripped gas is expected to drift into the Milky Way's outer halo, where it may help ignite fresh star formation in our own galaxy. The stream itself is not smooth. It is full of knots, clumps, and filaments, evidence of chaotic forces at work. Uneven gravity from the Milky Way tugs harder on some regions than others, while the thin, hot plasma of the Milky Way's circumgalactic medium pushes and wears away at the drifting gas. The result is a frayed, twisted pattern rather than a neat, even arc. Scenes like this, galaxies sharing, stealing, and reshaping each other's gas, are seen all across the distant universe. But those examples are often so far away that we can only glimpse their broad outlines. Here, in our own cosmic neighborhood, the Magellanic Clouds, the bridge, and the stream offer a close-up laboratory. With instruments such as the Australia Telescope Compact Array, the Parkes Radio Telescope, and precise star mapping missions in space, astronomers can track individual clouds of gas and individual stars, reconstructing when the clouds last brushed past one another and teasing out whether the stripped material came mainly from the small Magellanic Cloud, the large Magellanic Cloud, or both. Not all small galaxies caught by the Milky Way are as intact as the Magellanic Clouds. The Sagittarius dwarf galaxy is a fragile world already deep in the process of being torn apart. Unlike the Magellanic Clouds, which still hold themselves together, Sagittarius has been stretched into long, looping streams. It is a vivid example of galactic cannibalism, the slow devouring of one galaxy by another larger one. When astronomers first noticed the Sagittarius dwarf in the early 1990s, it was already far along in its undoing. Its stars were not gathered in a compact, rounded body. Instead, many had been pulled out into faint streams that wrap almost completely around the Milky Way, like a broken necklace whose beads have been scattered along an invisible string. The galaxy that once was is now more like a shredded ribbon, its original mass and brightness greatly diminished. Sagittarius follows a risky path, plunging through the Milky Way's disk rather than skirting safely around the outskirts. Each passage through the dense central regions exposes it to intense tidal forces. The Milky Way's gravity pulls more strongly on the side of Sagittarius nearest to us than on the far side, slowly prying its stars loose. With every orbit, more material is stripped away, leaving only a faint, shrinking core and ever longer streams behind. These streams are beautiful, and scientifically precious. They trace the shape of the Milky Way's gravitational field, acting like test particles scattered throughout the halo. By tracking their positions and motions, astronomers can map the distribution of mass in our galaxy, including the dark matter that cannot be seen directly. The slow destruction of the Sagittarius dwarf has become an unexpected gift, a natural experiment that reveals how the Milky Way works from the inside out. Some researchers suspect that each time Sagittarius has plunged through the Milky Way, it has also stirred up our galaxy's gas, compressing clouds and triggering bursts of star formation. If so, then the legacy of Sagittarius lies not only in the stars it has lost, but also in the stars it may have helped create new suns that now shine peacefully in the Milky Way's disk. The relationship between the two galaxies is both destructive and creative at once. Sagittarius is not alone in this fate. The Milky Way's halo contains many faint streams, remnants of other small galaxies, and ancient clusters that have already been digested. Each glowing trail marks the memory of a long-ago encounter. Sagittarius stands out because its unraveling is happening now, in cosmic terms, unfolding while we have the tools to watch. Today, what remains of its core orbits at a distance of tens of thousands of light years from the galactic center, it still barely qualifies as a galaxy, but only just. Over time, even this remnant will dissolve, its stars fully blended into the Milky Way. All of this sparks deeper questions. How many of the stars we see in the night sky were born in smaller galaxies that were swallowed long ago? How much of the Milky Way's current form is the result of quiet growth? And how much is the product of repeated feasts on its neighbors? The story of Sagittarius offers one clear lesson. Galaxies grow by merging and absorbing others, layer upon layer, until their histories are woven together. Far in the future, the Milky Way itself will collide with the Andromeda Galaxy, and the same basic process will play out on a grander scale. The faint streams from Sagittarius are, in a sense, early hints of that larger dance. Among the quieter companions of the Milky Way is the Fornax dwarf spheroidal galaxy, a modest, unassuming satellite drifting about 460,000 light-years away in the southern constellation of Fornax. To the eye, it is almost nothing at all, just a dim, hazy patch that can easily vanish into the deep black of the night sky. Hidden inside that small, hazy glow of the Fornax dwarf spheroidal galaxy is a quiet surprise. Fornax is home to not one or two, but at least 6 globular clusters, dense, ancient gatherings of stars that usually belong to much larger galaxies. For such a faint and fragile system, this is extraordinary. It has puzzled astronomers for decades, raising gentle questions about how a small galaxy like this could have formed, survived, and even kept such treasures while living in the shadow of a giant like the Milky Way. Globular clusters are among the oldest structures in the universe. Each one is like a glittering sphere made of hundreds of thousands of stars, all bound tightly by gravity. Many are older than 10 billion years, born when the universe itself was still young and rough-edged. In the Milky Way, more than 150 of these clusters float through the halo, their age and structure telling a story of endurance through cosmic upheaval. That is why Fornax stands out. A dwarf galaxy with only a few billion times the mass of the Sun should, by all expectations, struggle to form or hold on to even one such cluster. Yet Fornax keeps 6 of them in orbit, a number that rivals some medium-sized galaxies. These clusters sit at different distances around Fornax, like tiny jewels circling a dim lantern. Some remain close to the galaxy's heart, while others drift farther out as if they were hovering on the edge of escape. The stars inside them are like fossils. Many are extremely old and poor in heavy elements, suggesting that they formed when the universe had not yet been enriched by many generations of exploding stars. Their presence hints that, long ago, Fornax may have been richer in gas, more active, perhaps briefly blazing with bursts of star formation before settling into its current, quieter state. Unlike the Sagittarius dwarf galaxy, which is being torn apart by the Milky Way's gravity, Fornax appears calm and stable. Its stars are not being pulled into long streams, and its clusters remain bound. This suggests that Fornax follows a distant, gentle orbit around our galaxy, far enough away that the tidal forces are weaker. At roughly nearly 500,000 light-years from the Milky Way's center, it drifts in a region where it can preserve its fragile shape and its ancient companions. The abundance of globular clusters in Fornax also speaks to something we cannot see directly: its dark matter halo. To keep 6 massive clusters in stable orbits for billions of years, Fornax must sit in a deep, steady gravitational well. If it contained only the stars we can see, those clusters would likely have drifted away long ago. Their survival is strong evidence that Fornax is wrapped in a large, unseen sphere of dark matter, holding everything gently in place. There is another subtle clue. The clusters do not perfectly match the stars in Fornax's main body. The cluster stars tend to be older and poorer in heavy elements than many of the stars closer to the galaxy's center. This suggests that Fornax went through more than one wave of star formation, an early, intense phase that created the ancient clusters, followed by a later, slower phase that built up younger stars in its core. The clusters are like survivors from the first chapter of Fornax's story, while the rest of the galaxy shows how it slowly evolved afterward. Because of this unusual richness and its calm nature, Fornax has become a favorite target for both ground-based telescopes and space observatories. Deep images reveal layers of stars, very old red giants, and somewhat younger populations that formed only a few billion years ago. Unlike some dwarfs that seem almost frozen in time, Fornax has continued forming stars long after its birth, though never as furiously as a grand spiral. Its history feels like one of quiet, patient evolution rather than violent change. In contrast, the Sculptor and Sexton's dwarf galaxies offer a different face of galactic life. These are two small, unassuming companions of the Milky Way, orbiting at moderate distances and living much more quietly. The Sculptor dwarf galaxy lies a few 100,000 light-years away, discovered in the 1930s as a faint clustering of stars in the southern constellation of Sculptor. Even through telescopes, it remains subtle, easily lost among the Milky Way's foreground stars. Yet behind that faint smear lies a spheroidal galaxy containing only a few million stars. Most of Sculptor's stars are ancient. There is little sign that new ones have formed in a very long time. Its gas, the raw material for star formation, has either been stripped away by the Milky Way's gravity or used up long ago. The remaining stars are poor in heavy elements, telling astronomers that Sculptor formed its stars early, before many supernovae had time to enrich the gas. In a quiet way, it preserves the chemical memory of the young universe. The Sexton's dwarf galaxy, discovered much later, is even fainter and more elusive. It lies farther out, in the direction of the constellation Sextans, and is one of the dimmest galaxies known. Its stars are spread so thinly that the galaxy is only slightly brighter than the background sky. To detect it, astronomers had to patiently count faint stars one by one, finding a subtle overdensity where a small galaxy hides. Like Sculptor, Sextans is a dwarf spheroidal system with no spiral arms or glowing nebulae and almost no sign of ongoing star birth. It holds only a few 100,000 stars, most of them ancient and metal poor. At first glance, galaxies like Sculptor and Sextans might seem dull compared with dramatic systems that shine with young stars or are being torn apart. Yet their very calmness is valuable because they are not currently in the throes of destruction. Astronomers can study their internal structures with clarity. Their stars have remained relatively undisturbed for billions of years, allowing scientists to reconstruct a simple record of how they formed, how quickly they enriched their gas with heavy elements, and when star formation shut down. In cosmological simulations, small galaxies like these are thought to be some of the basic building blocks from which larger galaxies grow. Over time, dwarfs merge with each other, and with giants like the Milky Way, their stars ending up in the broad halos that surround big galaxies. By comparing surviving dwarfs such as Sculptor and Sextans with computer models, astronomers test whether their understanding of gas cooling, star formation, and gas loss is correct. If the models can reproduce galaxies like these, quiet, metal, poor, and simple, then there is more confidence in the larger picture of galaxy evolution. There is another class of dwarfs that carries an even stronger imprint of dark matter, galaxies like Draco and Ursa Minor in the northern sky. You would never notice them with your eyes alone. They hide near familiar constellations, so faint that even a very dark night does not betray their presence. Only deep imaging and sensitive detectors reveal them as fragile clouds of ancient stars scattered like dust across the black. Despite their ghostly appearance, Draco and Ursa Minor hold a powerful secret. They are overflowing with dark matter. In both galaxies, the invisible mass outweighs the visible stars by a large factor. Their mass-to-light ratios are enormous, meaning that for every bit of starlight we see, there is far more unseen matter holding the system together. They belong to the same dwarf spheroidal family, small, rounded systems with no gas, no bright nebulae, and almost no recent star formation. But in them, the role of dark matter becomes especially obvious. In the Milky Way, dark matter is mixed with stars, gas, and dust, making its presence harder to untangle. In Draco and Ursa Minor, where there is little else, the influence of dark matter stands out more clearly. By measuring how fast stars move within these tiny galaxies, astronomers can infer how much unseen mass is there and how it is distributed. This leads to some of the sharpest tests of our ideas about dark matter. The standard picture of cold dark matter suggests that halos should have very dense centers, with mass piling up toward the core. Yet observations of dwarfs like these often suggest flatter, more gently filled centers instead. That tension has inspired new questions. Do our models need refining? Or can events like repeated supernova explosions in the distant past push dark matter around and soften those peaks? Linked to this is the too big to fail problem. In simulations of the Milky Way's surroundings, many dark matter halos appear that are massive enough to host bright dwarf galaxies. But when astronomers search the sky, they find far fewer bright dwarfs than the models predict. It seems that some halos that should be capable of forming luminous galaxies remain almost entirely dark. Draco and Ursa Minor, dense yet dim, sit right in the middle of this debate, reminding us that the connection between dark matter and visible stars is not always straightforward. Over billions of years, the Milky Way's gravity has tugged on these dwarfs, stretching them and testing their resilience. And yet, unlike Sagittarius, they have not been fully torn apart. Their survival suggests that their dark matter halos are especially concentrated, acting as invisible armor against tidal forces. In a quiet way, they may be among the oldest survivors of the early universe, relics of the first small halos that later merged to build larger galaxies. Farther down the scale lie the so-called ultra-faint dwarfs, sometimes nicknamed after constellations like Boötes, where a few of the first were found. If the large and small Magellanic clouds are the bright, obvious companions of the Milky Way, then these ultra-faint dwarfs are their opposites. Not shining beacons, but fragile whispers of galaxies, so dim that even our most powerful telescopes struggle to see them at all, hiding just beyond the edge of visibility, like cosmic ghosts in the deep darkness of space. When astronomers first began to uncover these ultra-faint dwarfs, many quietly wondered whether they even deserved to be called galaxies. Some contain only a few thousand stars, sometimes only a few hundred, spread so thinly across space that they are like fading embers from a dying fire. The first clear glimpse came in the mid-2000s with the discovery of the Boötes dwarf galaxy. Among its family, Boötes 1 is the brightest, though even it is barely visible compared with modest systems like Fornax. Its stars are astonishingly old and chemically primitive, carrying the signatures of a universe that had barely begun to enrich itself with heavier elements. Soon after came Boötes 2, even smaller and fainter. It is so fragile that, for a time, astronomers were unsure whether it was a galaxy at all or simply a loose star cluster wandering at the edge of the Milky Way's halo. Its stars are widely scattered, and the system appears stretched by our galaxy's gravity. Yet when scientists measured how those stars move, they found something surprising. The total mass holding them together is far larger than the visible stars alone can explain. Boötes 2, it seems, is wrapped in a halo of dark matter. That invisible shell is what makes it a true galaxy, even if only a few stars remain to mark its presence. Discoveries like this open the door. As deep, careful sky surveys probe the Milky Way's outskirts, more and more of these ghostly companions appeared. They became known as ultra-faint dwarf galaxies, a fitting name for systems that seem to hover at the very edge of existence. Unlike brighter dwarfs such as Fornax, these galaxies do not show up as obvious smudges. Instead, astronomers sift through billions of stars, searching for tiny clumps of points that move together and share similar properties. Each new clump that passes these tests becomes another faint, ancient member of the Milky Way's extended family. Many of the stars in ultra-faint dwarfs are thought to have formed more than 12 billion years ago in the universe's first great wave of star formation after the Big Bang. Larger galaxies went on to form multiple generations of stars, enriching their gas with heavier elements over and over. The ultra-faint dwarfs did not. They seemed to have lit up briefly, then stopped, leaving their stars frozen in time, metal-poor and chemically simple, preserving a record of the universe's earliest conditions. Segue 1 is one of the most striking examples. It is so dim that it emits less light than a single bright star. For years, its nature was debated. Only when astronomers studied the motions of its stars did the truth emerge. Once again, there was far more mass than the starlight could account for. Dark matter must be present, holding the galaxy together. The stars themselves are among the most metal-poor ever found, relics of the first generations of star birth. Segue 1 is not just a ghost of a galaxy, it is a fossil from the dawn of cosmic history. Another tiny system, Reticulum 2, astonished astronomers for a different reason. Its stars showed unusual enrichments in very heavy elements that are forged in rare, violent events, such as neutron star mergers. For such a small, fragile galaxy to retain the debris from such explosions seemed unlikely. Yet, there it was, a tiny dwarf, holding the chemical memory of cataclysms that helped seed the universe with gold, platinum, and other heavy elements. Even the smallest galaxies, it seems, can carry records of the universe's most powerful events. Taken together, the ultra-faint dwarfs form a kind of mosaic of the early cosmos. The leading idea is that the smallest dark matter halos managed to form a few stars early on. But once the first generations of stars and early quasars lit up, their intense radiation heated and stripped gas from these tiny systems. Without gas, no new stars could form. The galaxies froze in place, their paltry handfuls of ancient stars drifting on, while larger halos retained their gas and continued to grow. In this way, ultra-faint dwarfs are survivors of a cosmic pruning, remnants from a time when only the biggest structures could keep shining. Even now, astronomers suspect that many more ultra-faint dwarfs remain hidden, buried in the faintest corners of the sky. Each new discovery brings theory and observation closer together, helping us understand not only the Milky Way's companions, but also how the first galaxies took shape. If you look toward the constellation of Canis Major, the Great Dog, you are peering into one of the more mysterious regions of our local universe. In that direction lies what is called the Canis Major overdensity, a curious clump of stars that does not fit easily into any category. It is not clearly a neat, separate dwarf galaxy like Sculptor or Sagittarius, nor is it obviously just part of the Milky Way's ordinary disk. Instead, it sits in a gray zone that has sparked lively debate. The story began when wide sky surveys mapped the distribution of stars across the galaxy. In the direction of Canis Major, astronomers found a dense patch of stars lying just beyond the thick plane of the Milky Way. These stars seemed to move in slightly different ways than nearby disk stars, hinting that they might belong to a separate system. The idea was thrilling. Perhaps we were seeing a small galaxy being swallowed, almost buried within the Milky Way itself. The discovery of a vast, faint arc of stars called the Monoceros Ring, looping around the outer disk, deepened the excitement. Some researchers suggested that this ring might be the torn remains of the Canis Major system, stretched out by our galaxy's gravity, much as the Sagittarius dwarf is being pulled into streams. For a while, it seemed clear, but as more data arrived, the picture grew more complicated. Other astronomers pointed out that the Milky Way's disk is not a flat, rigid plate. It is warped and rippled, like cloth stirred by passing hands. Such waves can create regions where stars appear denser along our line of sight, even if there is no separate galaxy present. The Canis Major overdensity, in this view, might be a natural ripple in the Milky Way's own disk, magnified by our perspective from within. The difficulty is that this region of sky is very crowded. Dust, gas, and millions of foreground stars lie between us and the structure in question. Untangling which stars belong to a possible satellite and which belong to the disk is extremely challenging. Some studies find stars that look older and poorer in heavy elements, more like those in typical dwarf galaxies. Others find that the stars resemble ordinary disk populations. The result is an ongoing, gentle tug-of-war of interpretations. Whether Canis Major turns out to be a devoured dwarf galaxy or a ripple in the Milky Way's own body, its study has already taught us something important. The boundaries between this galaxy and that galaxy are not always sharp. Rings, waves, and streams can all arise as galaxies interact. In a sense, The question, galaxy or ripple, may have more than one answer. A dwarf plunging through the disk long ago could have left behind both an overdensity of stars and ripples in the Milky Way's structure, blurring the line between object and footprint. To untangle puzzles like these, astronomers have turned to one of the most powerful tools ever launched into space, the Gaia mission of the European Space Agency. Gaia is more than a telescope. It is a precise measuring instrument that turns the sky into a vast, moving map. Its strength lies in the tiny shifts it can detect. As Earth orbits the Sun, nearby stars appear to shift their positions by minute amounts, an effect called parallax. The angle is so small that it is like noticing a single hair move at the distance of 1,000 kilometers. Yet Gaia measures it for over 1 billion stars. Gaia also records proper motion, the slow drift of stars across the sky, and, for many stars, radial velocity, the speed with which they move toward or away from us. When these measurements are combined, each star gains a 3-dimensional position and a 3-dimensional velocity, a full motion through space. With this information, astronomers can see not just where stars are, but how they travel, like dancers tracing graceful paths through the Milky Way. From Gaia's data, a new kind of science has blossomed: galactic archaeology. Instead of digging into the Earth, astronomers sift through star motions and chemical fingerprints to uncover the Milky Way's buried past. Before Gaia, many of the galaxy's faintest companions and most delicate stellar streams were invisible, blending into the background of billions of stars. With Gaia, patterns began to emerge, groups of stars moving together, sharing similar orbits and chemical signatures, suddenly stood out. One of the most dramatic stories to emerge is that of the Gaia-Enceladus merger. This was not a tiny dwarf quietly nibbling at the edge of the Milky Way. It appears to have been a substantial galaxy, perhaps a quarter the mass of the Milky Way at the time, that collided with our galaxy around 10 billion years ago. The evidence is subtle but powerful. Many stars in the halo move on long, plunging orbits, diving in and out of the galactic plane. Their chemical compositions show fewer heavy elements than stars that formed in the Milky Way's own disk. Together, their motions and chemistry mark them as the scattered remains of a once coherent galaxy that helped build the thick disk we see today. Gaia has also revealed stellar streams named after the astronomer Amina Helmi, groups of stars that travel together through the halo, no longer bound tightly but still following similar paths. Their shared orbits and chemical traits point back to a single dwarf galaxy that was devoured several billion years ago. On an ordinary map of the sky, these stars look like a random sprinkling. In Gaia's motion data, they line up like arrows, all pointing along the same invisible track. Even the Milky Way's main disk has been shown to ripple and bend. Some stars bob up and down through the plane, as if riding waves. These motions may be the lingering effects of past encounters with satellites, like the Sagittarius dwarf or other unseen companions that once plunged through the disk and disturbed its calm. The Milky Way, it turns out, is not a static, perfectly flat spiral. It is a living, trembling structure, still responding to the echoes of long-ago collisions. Gaia has changed how astronomers decide what is a galaxy, what is a cluster, and what is a stream. In the past, most discoveries came from spotting dense concentrations of stars in still images. Now, with motion added to the picture, some supposed galaxies have been reinterpreted as shredded remnants of larger systems, while some faint smudges in the halo have been confirmed as genuine dwarfs with shared orbits and histories. What once looked like a single photograph has become a moving film, and in that motion, relationships that were invisible before become clear. By combining Gaia's motion data with measurements of stellar chemistry, astronomers can now reconstruct much of the Milky Way's family tree. Stars born in large galaxies tend to be richer in metals. Those from smaller dwarfs tend to be poorer. When this information is layered over orbital paths, entire mergers can be identified and dated. The Gaia Enceladus stars point to a major collision in the deep past. Other named structures, with poetic names like Sequoia and Thamnos, trace their own swallowed galaxies. Each group of stars, drifting quietly through the halo, once belonged to a system with its own history and its own light. Gaia's map also sheds light on dark matter, the paths that stars follow, especially those in ancient streams and merger debris, reveal the shape of the Milky Way's invisible halo. If their orbits cannot be explained by the visible mass of stars and gas, then dark matter must be shaping their roots. By tracing these curves, astronomers probe the unseen skeleton that holds our galaxy together. With each new release of Gaia data, millions more stars are added, their motions measured more precisely. And with each newly identified stream or merger remnant, one more lost galaxy is recognized, not as a bright island in the sky, but as a scattered family of stars now woven into the Milky Way's fabric, drifting on together through the dark. The faint dwarf galaxies we see today, like Sculptor and Fornax, are only the survivors of a much larger family. Many of their cousins vanished long ago, pulled apart and stirred into the Milky Way, leaving behind only thin streams, ripples, and odd motions for us to decode. When astronomers study these tiny systems, one puzzle returns again and again: the strange way dark matter seems to arrange itself inside them. Our theories and computer simulations say one thing. The sky, quietly, often says another. This mismatch is known as the cusp core problem. In the standard picture of cold, dark matter, the invisible particles gather very densely toward a galaxy's center, forming a steep, pointed rise in density called a cusp. But when astronomers look closely at many real dwarf galaxies and trace how their stars move, they often find a smooth, flattened central region instead, something more like a core. It is a bit like the difference between walking up a sharp hill and walking across a broad plateau. A cusp is the steep slope rising abruptly toward a peak. A core is the gentle, nearly level top before the land begins to fall away. In large galaxies like the Milky Way, the situation is tangled because stars, gas, and central black holes all stir the gravitational field. Dwarfs are simpler, with little visible matter to complicate things. Dark matter's influence stands out more clearly, and again, their inner regions look more like cores than cusps. For pure cold, collisionless dark matter, sharp cusps should form naturally. The fact that many dwarfs appear to have cores suggests that something in the story is missing. Either our picture of how galaxies grow is incomplete, or dark matter itself has subtler behavior than we once imagined. One path to an answer looks not to new particles, but to the messy lives of galaxies. Even a small dwarf can be shaken by its own stars. When massive stars reach the end of their lives and explode as supernovae, they pump enormous energy into their surroundings, pushing gas outward from the central regions. If this happens repeatedly over millions or billions of years, the gravitational pull in the inner galaxy fluctuates. Dark matter responds to those changing tugs. Bit by bit, the sharp central peak can be softened, spreading into a flatter core. Modern simulations that include not just dark matter but also gas, stars, and feedback from their births and deaths often produce dwarfs with cores that look a great deal like what we observe. Yet not everyone is convinced that star formation alone can solve the puzzle. Some dwarf galaxies show clear signs of cores despite having very little recent star formation. And in a few cases, the amount of energy required from supernovae seems uncomfortably large for such small systems. For those galaxies, feedback may not be enough. This leads to more radical ideas. Perhaps dark matter is not quite as cold and as simple as we thought. One possibility is called self-interacting dark matter. In this picture, dark matter particles can occasionally nudge or scatter off one another, albeit very gently. Over long periods, these tiny interactions can help move particles around and soften sharp cusps into smoother cores without tearing apart the overall halo. Another idea imagines dark matter as made of extremely light, wave-like particles. In this fuzzy dark matter scenario, the quantum nature of the particles causes them to spread out and resist forming tight central spikes, again giving naturally soft cores. These alternatives are appealing because they can, in principle, explain the inner shapes of dwarf galaxies without requiring furious early bursts of star formation, but they come with their own constraints. If dark matter interacts too strongly, or if its wave nature is too pronounced, it could spoil the good agreement between theory and observation on larger scales, where cusps seem less of a problem. So, theorists have to walk carefully, tuning ideas so they fix the small without breaking the large. Meanwhile, observations keep getting better. With modern spectrographs and careful measurements of stellar motions, astronomers can map how mass is distributed inside faint dwarfs in increasing detail. Radio telescopes trace the dance of cold gas, adding another layer of information. The result is not a simple, tidy picture. Some dwarfs clearly show smooth cores, others appear to be more sharply peaked, closer to cusps. This variety hints that there may not be a single, universal answer. A galaxy that lived through violent early starbursts might well have flattened its inner dark matter. Another that evolved more gently, or lost its gas early, might still carry its original cusp. The cusp core problem, then, becomes less a contradiction and more a window into the different life stories small galaxies can have. Far from the bright band of the Milky Way's disk, another story is written in softer light. The galactic halo stretches out in all directions, a faint sphere reaching far beyond the visible spiral. At first glance, it seems almost empty, a thin mist of stars against darkness. But hidden in that dim glow is the Milky Way's memory. The halo is made of lonely stars, old globular clusters, and the remnants of galaxies that once drifted freely before being captured. Most astronomers now agree that much of the outer halo did not form in place. It was built from the wreckage of many smaller galaxies that were pulled apart and absorbed over billions of years. The idea is simple and powerful. The halo is a graveyard of long-lost dwarfs. Hints of this appeared decades ago, when it became clear that halo stars looked very different from the stars in the disk. Halo stars are, on average, very old and very poor in heavy elements. In the Milky Way's disk, by contrast, stars are younger and richer in metals. Their repeated cycles of star formation and supernova explosions have steadily enriched the gas. The halo, by comparison, looks frozen in time, as if little has changed in many billions of years. Dwarf galaxies offer a natural way to explain this. They are small and fragile. Many lose their gas early and stop forming stars. Their stars remain chemically simple, poor in heavy elements. When a massive galaxy like the Milky Way captures such a dwarf and tears it apart, its ancient, metal-poor stars are sprinkled through the halo. Over many such events, the halo fills with exactly the kind of stars we see today: old, faint, and chemically primitive. As surveys improved, astronomers began to see the scars of these feasts directly: long, curving streams of stars wrapping around the sky, odd clumps moving on unusual orbits, globular clusters whose chemistry did not match typical Milky Way stars. These features are like faded stitches in a cosmic quilt. Each one marks a galaxy that once was whole. Over time, streams blur and clumps disperse, but the process is so slow that even after 10 or more billion years, many traces remain. By measuring how halo stars move and what elements they contain, scientists can sort them into families. Some share the same orbital paths and chemical signatures, revealing that they were born in the same long-vanished dwarf. In this way, the halo becomes a vast archive. Each star and cluster is a piece of evidence, and taken together they show that the Milky Way grew not by gentle swelling alone, but by swallowing countless smaller systems whose identities are now woven into its outskirts. Computer simulations echo this story. Large galaxies in those digital universes grow by merging with and devouring smaller ones, their halos thickening with each meal. Many of the halo's globular clusters seem to be immigrants as well, still intact even though their parent galaxies are gone. Their orbits and chemistry allow astronomers to group them into former families, clusters that once circled in the same dwarf before being brought in together. Even the Milky Way's dark matter halo carries this history. When a dwarf galaxy falls in, its dark matter halo merges with our own, thickening the invisible skeleton that holds the galaxy together. If most of the halo came from such mergers, then the structure that shapes the orbits of halo stars today is itself a monument built from long-consumed galaxies. Within these remnants, the stars of dwarf galaxies whisper an even finer story. Their chemical fingerprints often differ from what we see in the Milky Way. One of the clearest differences appears in the balance between so-called alpha elements: magnesium, calcium, silicon, and others, and iron. In the Milky Way, old stars tend to show high amounts of alpha elements compared with iron. That is because in our galaxy's early days, massive stars dominated. They lived briefly, exploded as core collapse supernovae, and flooded space with alpha elements. Only later did a different kind of explosion, Type 1, a supernovae from smaller, longer-lived stars, begin adding large amounts of iron, slowly changing the ratio. In many dwarf galaxies, this transition happens at much lower overall metallicity, when the stars still contain very little of any heavy elements. That tells astronomers that dwarfs form stars much more slowly and less efficiently, because their star formation is gentle and stretched out. Type 1, a supernovae begin to influence their chemistry sooner. Their alpha to iron ratios drop earlier. Each dwarf thus keeps a record of its own quiet, uneven growth. When stars from such systems are later found in the Milky Way halo, their unusual chemical balance betrays their foreign birth. Even heavier elements, beyond iron, add more detail. These elements are made in two main ways. In the slow, or S process, they build up gradually inside aging giant stars. In the rapid, or RR process, they are forged in sudden violent events such as the merger of neutron stars or certain very powerful supernovae. Dwarf galaxies show a wide range of patterns in these heavy elements. Some contain almost none, suggesting that those rare, violent events hardly ever happen there. Others show sudden, dramatic spikes in raw process material, as if a single catastrophic event once flooded the entire small galaxy with newly forged heavy elements. Reticulum 2 is one of the most striking cases. This ultra-faint dwarf contains stars unusually rich in R-process elements. The simplest explanation is that long ago, a single neutron star merger occurred there, and because the galaxy was so small, the debris from that one event enriched nearly all of its remaining gas. Every star born afterward carried the chemical echo of that single explosion. In a big galaxy like the Milky Way, such a signal would quickly be diluted and lost in the crowd. In a tiny dwarf, it stands out clearly, even after billions of years. Because dwarfs are small and often form stars in brief bursts separated by long, quiet periods, their chemistry develops in a stop-start rhythm. A short episode of vigorous star formation can blow out much of the gas, shutting the process down. During the pause, existing stars age and die, slowly changing the composition of the remaining gas. When star formation resumes, the next generation is born with a noticeably different chemical signature. Over time, this on and off pattern creates the strange and beautiful element ratios we see today. Astronomers use these patterns as a kind of tag. Stars born from the same cloud of gas share the same detailed chemical fingerprint. In the crowded Milky Way, it is hard to trace such families because so many different environments overlap. In small dwarfs, where the populations are simpler and more distinct, it becomes easier. By comparing the chemistry of stars in dwarf galaxies with that of stars in the Milky Way's halo, scientists can pick out those that were once neighbors, even if they are now spread across the sky. Large spectroscopic surveys are now measuring the elemental abundances of millions of stars. When combined with precise motions from missions like Gaia, these chemical fingerprints allow astronomers to build an ever-clearer family tree for our galaxy and its companions. Dwarf galaxies, with their extreme and sometimes odd mixtures of elements, have become key pieces in this puzzle. They help us understand how galaxies grow, how dark matter shapes them, how stars forge the elements, and how the simple early universe slowly turned into the rich, diverse cosmos we see today. Even after all this, the Milky Way's story still feels unfinished. Around our galaxy, out in the dim outskirts of the halo, astronomers suspect that many more tiny companions are hiding in the dark. Some may be too faint, some too spread out, and some simply lost behind the bright river of the Milky Way's own stars and dust. To find them, scientists need gentler, sharper eyes, deeper surveys, better telescopes, and clever ways of listening for patterns that are almost swallowed by noise. Instead of searching only for obvious bright patches, they look for small gatherings of stars that move together and share similar ages and chemistries, like a soft whisper of order in the background. Each new dwarf galaxy that emerges from the data quietly reshapes our sense of how the Milky Way grew, how its stars assembled, and how dark matter sculpted our neighborhood. If current predictions are right, most of our galaxy's satellites have not yet been seen. New sky surveys will help fill in some of those missing pieces. Astronomers are especially hopeful about the Vera Rubin Observatory, whose repeated scans of the sky are expected to reveal ultra-faint dwarfs that earlier surveys missed, especially those hiding near the Milky Way's bright band. Infrared telescopes help too, by seeing through dust that blocks ordinary starlight. But even these careful searches may only uncover part of the hidden population, because some of the missing dwarfs may be more than faint. They may be almost completely dark. In these ghostly systems, dark matter would so overwhelmingly outweigh normal matter that only a few stars, perhaps none at all, would shine. No image would betray them. The only way to sense their presence would be through their gravity, in the subtle ways they tug on stellar streams, bend the paths of wandering stars, or disturb the smooth motion of gas at the Milky Way's edge. Already we know that dwarf galaxies can be extreme. Segue 1, for example, holds fewer stars than a typical globular cluster, yet seems to be dominated by dark matter. Crater 2 is enormous, but so diffuse that its stars barely brighten the sky at all. Together they show that the missing satellites are not one simple kind of object, but a varied and delicate family. The search extends beyond our galaxy. Andromeda has its own retinue of dwarfs, some arranged in puzzling thin planes like beads on invisible strings. The Triangulum galaxy also appears to have fewer satellites than theory would suggest. If this shortage shows up around many galaxies, the mystery of missing dwarfs is not just local. It becomes a clue to how small galaxies form and survive throughout the universe. Only a little more than 1 century ago, no one even knew dwarf galaxies existed. As telescopes improved and wide surveys swept the sky, these tiny companions appeared one by one. Each new generation of instruments has peeled back another layer, revealing ever fainter systems. Our picture of the universe is always unfinished. The galaxies we have not yet found may simply be waiting for the next gentle step forward in our ability to see. Some of the missing dwarfs may not be missing at all. They may already have been unmade by the Milky Way and Andromeda, their stars stretched into thin streams in the halo, their dark matter folded into the larger halos of their captors. In that sense, they are not gone, only dissolved. Their light and mass are now spread out, no longer recognizable as separate worlds. The first step in this soft erasure is often the loss of gas. Gas is the breath of a galaxy, the fuel for new stars. Without it, star formation slows, then stops, and the galaxy fades into a quiet swarm of aging suns. Many dwarfs near the Milky Way are almost completely gas-free, looking bare and exhausted, compared with the bright spirals we picture when we hear the word galaxy. One important way they lose this lifeblood is through ram pressure stripping. Imagine riding in a car with the windows open and feeling the wind tug at everything inside. Now replace the car with a small galaxy, and the air with the thin, hot gas that fills the space between galaxies. As the dwarf moves through this medium, its own gas feels the pressure. If the galaxy plunges through the hot halo that surrounds a giant like the Milky Way, the force can be strong enough to blow much of its gas away. The heavier stars mostly stay put, but the light, fragile gas is peeled off and left trailing behind. Gravity shapes dwarfs in another way, through tidal stripping. When a small galaxy orbits a much larger one, the nearer side feels a stronger pull than the far side. Over time, this difference tugs stars and gas loose, stretching the dwarf into streams. Often a small, dense core survives, still clinging to a few stars, while the outer layers are stripped like the peel of a fruit. What remains is a faint, ghost-like remnant following its giant companion, a shadow of what it once was. Stars can help to drive gas out from within. Massive young stars shower their surroundings with intense light and stellar winds. Then, as they die, they explode as supernovae, sending shock waves through the galaxy. In a large system, gravity can reclaim much of the gas pushed outward. In a small dwarf, the pull is weaker. Gas driven to the outskirts can be more easily lost to ram pressure and tides. In this way, the very process of star formation gradually undermines the dwarf's ability to form more stars in the future. In the local group, we can watch this slow unmaking with unusual clarity. Satellites such as Sculptor, Draco, and Ursa Minor orbit close to the Milky Way and show signs of repeated stripping until little remains but ancient stars. Around Andromeda, long arcs of stars mark where dwarfs have been torn apart and scattered through its outer halo. Over billions of years, these processes act almost like a quiet natural selection. Dwarfs that stay far away may keep their gas and continue forming stars. Those that dive deep into a giant's halo risk losing everything and fading into ultra-faint remnants that barely hold together. These remnants raise another gentle question. If the Milky Way can have satellites, could some of those satellites have satellites of their own? Could there be galaxies, orbiting galaxies, that orbit galaxies, a hierarchy one level deeper than we usually picture? In computer simulations of the universe, dark matter naturally forms structures inside structures. Large halos host big galaxies. Within them, smaller halos form, each able to host a dwarf. Within those smaller halos, tinier clumps appear, like nested shells. In that sense, there is nothing to stop a dwarf galaxy such as Fornax or Sculptor from having its own miniature companions. In theory, finding such sub-satellites would be extraordinarily hard. Even the Milky Way's known dwarfs are faint and elusive. A dwarf's dwarf would be fainter still, perhaps containing only a few hundred stars. Some might be completely dark, never having formed stars at all. Only their gravity would reveal them in subtle tugs on nearby stars or delicate twists in tidal streams. There are hints that this layered structure may already be with us. The large and small Magellanic Clouds, themselves satellites of the Milky Way, are surrounded by tiny, faint systems that may be their own companions rather than ours. If that is confirmed, then we are already seeing galaxies that are, in effect, satellites of satellites. Some of the stars and gas being drawn into the Magellanic Stream may have begun in those even smaller systems, only to be swept up into a larger dance. For a small satellite like Draco to keep its own tiny partner, that partner would need to orbit very close to its parent, staying within the protective grip of its dark matter halo, so the Milky Way could not easily steal it away. Its light, if it had any, would blend into the dwarf's faint glow, almost impossible to distinguish by eye. Astronomers would have to rely on motion, searching for little knots of stars drifting together in unusual patterns. Some of these hypothetical sub-satellites might never form stars at all. Their halos could be too small to hold on to gas against heating, winds, and stripping. They would be completely dark, detectable only through the way they disturb nearby orbits. In that case, our picture of the cosmic hierarchy would extend one step further into the unseen. It is a question that rhymes with one we once asked closer to home. Planets have moons. Could moons have moons? The answer turned out to be sometimes, but only under special conditions. On the scale of galaxies, gravity seems to favor nesting, too. Galaxies live inside halos, halos inside larger halos, chains of structure repeating from the smallest scales to the largest. Whether that chain truly continues one level down from satellites to satellites of satellites remains an open, quiet question, hanging in the dark and waiting for future eyes to bring it into view. Perhaps, in the quiet decades ahead, as our instruments grow more sensitive and we learn to listen for ever fainter motions, the universe will gently reveal how deep this nesting of structures truly goes. In our nearby corner of space, the local group, two great spirals rule the scene: the Milky Way and the Andromeda Galaxy. They are often pictured as twins, each wrapped in sweeping arms of stars, gas, and dust, each surrounded by a crowd of much smaller companions. From a distance they look serene, gliding through the dark. But both are slowly falling toward one another, destined to meet and merge in a few billion years, their graceful shapes reshuffled into something new. At first glance they seem almost equal. Yet, when astronomers look at their families of dwarf galaxies, the balance shifts. Around the Milky Way, roughly 60 satellites are known, most of them extremely faint, ancient dwarfs like Draco and Ursa Minor, where star formation ended long ago. Around Andromeda, at least 90 companions have been identified, and there are hints of more. Some of that difference may come from our awkward vantage point. We live inside the Milky Way, peering through curtains of dust and dense star fields that hide its faintest neighbors. Andromeda, by contrast, is seen from the outside, its entourage scattered around it like softly glowing fireflies. Even after correcting for this, Andromeda truly seems to host a richer collection. It has bright, compact companions like M32 and M110. M32 may be the stripped core of a once larger galaxy, its outer layers torn away by Andromeda's gravity. M110 carries signs of repeated bursts of star formation, perhaps sparked by close brushes with its massive parent. Many of Andromeda's smaller dwarfs have chemical patterns different from those around the Milky Way, as if they followed slower, more varied histories of star birth and enrichment. One of the strangest features of Andromeda's family is the way many satellites seem to lie in a single thin plane, a huge, almost disk-like sheet of dwarf galaxies moving together. This is not what simple dark matter simulations usually predict, which is a more spherical cloud of satellites. The alignment may be a coincidence, or it may be a clue that groups of dwarfs fell in together rather than one by one. The Milky Way's dwarfs look more scattered, though even here there are hints of gentler patterns and arcs. Brightness complicates the comparison. Some Milky Way satellites, the so-called ultra-faint dwarfs, contain only a few thousand stars and are barely detectable even though they lie close to us. At Andromeda's distance of about 2.5 million light-years, galaxies that fragile are almost impossible to see with current instruments. Future telescopes may find more of them. If they do, the apparent imbalance between the two giants could fade. If they do not, then some deeper difference in how their halos gave rise to stars may be at work. The Milky Way also has something Andromeda does not: two bright, gas-rich, irregular companions, the Large Magellanic Cloud and the Small Magellanic Cloud. Each is massive enough to host star formation on a grand scale and may even carry its own tiny satellites. Their motion through our halo has pulled out a long ribbon of gas called the Magellanic Stream, wrapping partway around the sky. Andromeda has no obvious equivalent pair, though its companion M32 may be a different echo of the same theme, a smaller galaxy reshaped by a giant's pull. Taken together, these differences turn the Milky Way and Andromeda into a kind of natural experiment. They are similar in mass and age, brothers in the same small group, yet their families of satellites tell different stories. By comparing them, astronomers can ask gentle but deep questions. Are the differences mainly due to where we sit and how we look? Are they the result of different cosmic neighborhoods and merger histories? Or do they hint that our models of dark matter and galaxy formation need subtle adjustment? The local group itself is a quiet theater for this long play. It contains three main spirals: the Milky Way, Andromeda, and the smaller but still impressive Triangulum Galaxy, along with more than 80 dwarf galaxies of many shapes and brightnesses. It is not as crowded and violent as a giant galaxy cluster, where collisions happen constantly, nor as empty as the vast cosmic voids. Instead, it is a gentle middle ground, close enough that telescopes can resolve individual stars in many of its members. Because these galaxies are so near, astronomers can trace the orbits of dwarfs around both the Milky Way and Andromeda, map the motions of Triangulum, and see how groups of small galaxies may have fallen in together. Some dwarfs still carry chemical fingerprints from very early times. Others show evidence of later bursts of star formation or past collisions. Within this modest space, theories about dark matter, star formation, and tidal stripping can be tested in detail before being applied to galaxies far away. Triangulum's presence adds a third voice to the conversation. It is less massive than the two giants, but still large enough to host its own faint companions. Comparing its satellites with those around the Milky Way and Andromeda lets astronomers see which patterns repeat and which seem unique. If similar puzzles appear around all three spirals, they are likely woven into the deeper fabric of cosmology. If not, environment and history may be playing a larger role than we thought. The local group is not frozen. The Milky Way and Andromeda are slowly spiraling toward each other and are expected to have their first close pass in roughly 4 billion years, with a full merger a few billion years after that. Triangulum may be pulled into this embrace as well. Dwarfs will be stripped, shuffled, or scattered. Some will dissolve into tidal streams, while others survive in new paths around the remnant supergalaxy. In the background of this grand future, the fate of the Magellanic Clouds adds a quieter layer of intrigue. The Large Magellanic Cloud, in particular, is surprisingly massive. Wrapped in a deep halo of dark matter, it is heavy enough to tug on the Milky Way's motion and gently warp our own halo. This means it is not just a minor bystander. It is an active partner in shaping our galaxy's near future. Its orbit is slowly decaying. Many simulations suggest that in roughly 2 to 3 billion years, the Large Magellanic Cloud may spiral inward and merge with the Milky Way long before Andromeda arrives. If that happens, the cloud's stars and gas will become part of our galaxy's disk and halo, feeding new star formation, stirring the outer regions, and leaving stellar streams as quiet signatures of the merger. The small Magellanic Cloud, bound to its larger neighbor, might follow it in, drawn inward by their shared gravity. In that scenario, by the time the Milky Way meets Andromeda, the Magellanic Clouds as separate galaxies will already be gone, their identities dissolved into the larger system. The Great Collision would then be between a Milky Way that has already grown heavier and richer, and Andromeda approaching from afar. But the universe is generous with possibilities. If the Magellanic Clouds survive as distinct systems until the Milky Way and Andromeda encounter, their fate becomes more uncertain. The overlapping tides of two giant halos could fling them into wild new orbits, send them looping far out before drawing them back, or even eject them completely, turning them into wandering dwarfs, drifting alone through the local group. In some computer models of galaxy mergers, small satellites are not gently absorbed. They are slingshotted away by the shifting gravitational field, like stones flicked from a spinning sling. It is also possible that, in the chaos of the merger, one or both clouds could become more closely bound to the newly formed remnant, sometimes nicknamed Milkomeda or Milka. In that case, their stars and gas would end up deep inside the new giant, recognizable only to those who know how to read the fossil trails in its halo. Despite the dramatic language, a galaxy collision is not a violent smash in the everyday sense. Stars are so widely separated that almost none will actually collide. The true drama belongs to gravity and gas. Orbits will be reshaped. Great flows of interstellar gas will be funneled toward the centers of the merging galaxies. Bursts of new star formation will flare where that gas is compressed. The large and small Magellanic clouds, both rich in gas today, could serve as extra fuel for those future starbursts if they still retain their reservoirs when the encounter peaks. The sturdy dark matter halo around the large Magellanic cloud may let a dense core of it survive, even as its outer stars are stripped away. Long after the merger, a careful observer might still find a compact knot of stars and dark matter at the heart of the remnant, a quiet fossil of a small galaxy that once circled our own, far in the future. If any eyes are still watching from what was once the Milky Way, or from some world born in the merged supergalaxy, the night sky will look utterly different. The graceful band of the Milky Way will have been replaced by a complex tangle of star clouds, arcs, and ripples. Yet hidden in that brightness will be the blended legacies of many worlds. Stars from Andromeda, from Triangulum, from long-devoured dwarfs, and from the large and small Magellanic clouds. Two small, restless galaxies that, for a while, circled our own and then quietly gave their light to the future shape of the cosmos. But this raises a quiet, lingering question. Can the smallest galaxies ever slip free from the giants that hold them? At first, it seems unlikely. A massive galaxy bends space around itself like a deep well, and its tiny companions, the dwarf galaxies, circle inside that well as if there were no escape. The giant pulls at their gas and stars, stretches their shapes, and in time may swallow them completely. Yet gravity is not a fixed cage. It shifts as galaxies move, collide, and trade energy with one another. In that slow choreography, not every companion is doomed to fall inward. Some may find the right push at the right moment and drift away, becoming quiet wanderers between the giants. To see how this can happen, it helps to think about escape velocity. Every massive object, from a planet to a galaxy, has a speed that must be reached to break free of its pull. A spacecraft leaving Earth must climb to roughly 11 kilometers per second. Near the Sun's position inside the Milky Way, a star or a dwarf galaxy would need a speed of around 550 kilometers per second to escape the galaxy's halo. Most dwarfs do not come close to that. They move slowly along their orbits, safely bound. But special circumstances can change their fate. When two large galaxies approach or merge, their gravity fields twist together and become tangled. In that storm of forces, some small satellites are pulled inward and torn apart. Others are flung outward, gaining so much energy that they drift away into the dark, not destroyed, but exiled. Computer simulations show miniature galaxies tossed out like this into intergalactic space, no longer tied to any single master. There is also the graceful trick of the gravitational slingshot. Spacecraft use this when they swing past a planet and steal a little of its orbital energy, leaving with a higher speed than they arrived. A dwarf galaxy can experience something similar. If it passes close to a massive neighbor at just the right angle, the encounter can add energy to its orbit instead of robbing it. Its path stretches, becoming wider and more elongated. In rare cases, that new orbit may carry it beyond the reach of its original host entirely. Astronomers have seen hints of this in the real universe. In certain small galaxy pairs, one member plunges toward a giant, while the other is flung outward at surprising speed. In some nearby regions of space, tiny galaxies are observed moving so fast that they should be escaping the pull of entire clusters. If dwarfs can be ejected from such crowded environments, they can almost certainly be thrown out of individual galactic halos as well. Even in our own neighborhood, the story is not settled. For many years, astronomers debated whether the large and small Magellanic Clouds are long-term satellites of the Milky Way or recent visitors. Precise measurements of their motion show that they are moving faster than expected if they were deeply settled in our galaxy's halo. Depending on how massive and extended that halo truly is, the clouds may either spiral inward and merge with the Milky Way, or eventually drift away, slipping out along stretched orbits. If they stay, their gas and stars will be folded into our galaxy's disk and halo. If they leave, they could become solitary wanderers in the local group, perhaps to be tugged later by Andromeda, or to roam for billions of years in the quiet space between. The deciding factor is the true shape and mass of the Milky Way's dark matter halo, the invisible cocoon that surrounds us. If that halo is larger and heavier than we think, escape becomes far more difficult. If it is smaller or more compact, freedom is easier to reach. Because the halo itself cannot be seen directly, the fate of the Magellanic Clouds remains an open, gently humming question. Even when a dwarf cannot escape whole, pieces of it can. Stars pulled away by tidal forces flow into long, faint streams that wrap around their host. Some of these delicate rivers of light may drift beyond the edge of the halo, becoming intergalactic threads. They are the stretched-out ghosts of once intact galaxies, still moving together long after their original shapes have been unmade. In the early universe, when galaxies were smaller and packed more closely together, such encounters were far more common. Tiny dwarfs were tossed about, captured, traded, and ejected as larger systems grew. Some of the lonely dwarfs we see today, drifting far from any giant, may be these ancient escapees. Their stars remember only a quiet present, but their motions tell of old battles and long-forgotten collisions. Even if a dwarf escapes a single halo, it does not necessarily leave the family. The Milky Way, Andromeda, Triangulum, and their many companions share a broader gravitational field called the local group. A rogue dwarf can leave one galaxy's embrace and still remain bound to this larger structure, circling slowly through the shared space of the group. In that sense, escape is always relative. A galaxy can leave home and still remain part of the wider community, wandering for ages until a new encounter claims it. As our instruments sharpen, these small galaxies are moving from the margins of astronomy toward the center of the story. For much of the last century, dwarfs were treated as minor characters. They were faint, fragile, and difficult to study, overshadowed by great spirals and giant ellipticals. Now they are recognized as essential clues to how galaxies assemble and how dark matter shapes the universe on small scales. The main difficulty has always been simply seeing them. A dwarf galaxy can contain only a few million stars or fewer, scattered so thinly that they vanish into the background. Its entire light can be less than that of a single bright star. To find such a whisper against the sky, astronomers need wide, deep surveys and patient analysis. A new generation of observatories is poised to transform that search. The Vera C. Rubin Observatory, with its wide-field camera, will scan the southern sky again and again, stacking countless images together. Over the years, very faint smudges that are invisible in a single exposure will build up into detectable patterns. Patches of sky that now look empty may reveal hidden gatherings of stars, the faintest members of the local group. Above the blur of Earth's atmosphere, space telescopes will step in to sharpen the picture. The Nancy Grace Roman Space Telescope will be able to zoom in on dwarf candidates with clarity close to that of the Hubble Space Telescope, but across much wider fields. It will help confirm which star groupings are true galaxies, show whether they have central clusters or faint streams, and search for subtle signs of past interactions. The James Webb Space Telescope will look deeper into their inner lives, especially in infrared light. Its sensitivity makes it possible to pick out ancient, cool stars and to peer through thin veils of dust. Some of the faint dwarfs it studies nearby will resemble the first building blocks of galaxies in the early universe. Others will reveal long, quiet histories, with stars that span nearly the entire age of the cosmos. Radio observatories will map the hydrogen gas in and around dwarfs, showing which ones still have fuel for new stars and which have been stripped bare by larger neighbors. Extremely large telescopes on the ground, with mirrors tens of meters across, will separate their stars and measure their motions, turning faint blurs into detailed systems. Even high-energy observatories will play a part, watching how supernova explosions and small black holes stir and heat the gas inside these dwarfs. With all these tools working together, astronomers expect to find not just more dwarfs, but stranger ones. Some may be ultra-diffuse galaxies, where a small number of stars spread across enormous volumes, making them nearly invisible. Others may be unusually rich in gas, yet heavily veiled, or ancient relics that never grew beyond a single early burst of star formation. Each new type will refine or challenge our ideas about how galaxies form and fade. As the census of dwarfs grows, the puzzle will shift from "where are they?" to "what do they mean?" Instead of chasing a handful of elusive galaxies, scientists may soon face thousands, each with its own history, orbit, and chemical fingerprint. Weaving that many threads into a coherent story of cosmic evolution will be demanding, but also deeply rewarding. Every tiny galaxy carries a piece of the universe's memory, and within that memory lies another question, softer and more personal. Could any of these small galaxies host life? When we imagine life in the universe, our minds often jump to grand spirals like the Milky Way. Their wide disks and thick halos hold hundreds of billions of stars, along with rich supplies of heavy elements needed for rocky planets and complex chemistry. Their size offers variety and a kind of averaged-out stability. Somewhere amid their countless suns, it feels reasonable to hope for calm, life-friendly worlds. Dwarf galaxies, by comparison, seem less promising. Many contain only a few million stars, or fewer. Some ultra-faint dwarfs may hold no more than a few thousand suns. Fewer stars mean fewer chances for planetary systems that resemble our own. Their shallow gravity wells struggle to hold on to the heavy elements released by supernova explosions. Much of that precious material may simply drift away, leaving stars and clouds that are chemically primitive. Heavy elements like carbon, oxygen, nitrogen, silicon, and iron are the bones and blood of rocky planets and living chemistry. Without enough of them, planets may be mostly gas and ice, or might not form at all. In many dwarfs, the overall level of these elements remains low, even after billions of years. That makes Earth-like worlds, as we understand them, less likely. Dwarf galaxies are also more exposed. Lacking thick disks and dense gas layers, they offer little shielding from harsh radiation. A nearby supernova or gamma-ray burst can wash a large fraction of the galaxy in damaging light, stripping atmospheres or sterilizing young worlds. In a small system, a single catastrophic event touches a larger fraction of all potential habitats. And yet, even here, possibilities remain. Not every star has to be sun-like. Low-mass red dwarfs burn quietly and steadily for trillions of years, far longer than stars like our Sunday. Around such stars, even in a small or metal-poor galaxy, there might still be enough heavy elements in a local cloud to form one or two rocky planets. If those worlds can hold onto atmospheres and water, they could have unimaginably long spans of time in which life might arise. As some dwarf galaxies lose their gas to stripping and internal explosions, their chaotic youth settles. Massive, short-lived stars die off. The remaining population becomes older and quieter. In that long twilight, star formation slows or stops, but existing planetary systems can enjoy extended stability. A galaxy that looks dead from far away may still cradle a few worlds where conditions remain gentle for billions of years. The oldest dwarfs preserve chemical patterns from near the dawn of time. Any rocky planets around their stars would be ancient beyond our experience, older than Earth by many billions of years. If life ever began there and survived the hazards, it would have had a head start that stretches the imagination. On the other hand, the fragility of these galaxies means that many such worlds would be lost as their hosts are torn apart. When a dwarf finally succumbs to the pull of a giant, its gas and many of its stars are stripped and spread into the host's halo and outer disk. But stars are resilient. A planet tied to a long-lived star can remain in orbit even as its galaxy dissolves around it. What was once a world in a faint dwarf may end up circling quietly inside the halo of a larger galaxy, its sky now filled with a different pattern of distant suns. So, even in destruction, the story continues. Dwarf galaxies may be fragile, but they are also the seeds and threads from which larger structures are woven. If any of their planets ever cradle life, those living worlds may travel with their stars, crossing from one galactic environment into another, carrying with them the silent memory of the small, dim homes where their stories first began.